Good morning, everyone. You're listening to the Sci-Files, an exposure segment featuring Michigan State University student research. We're your co-hosts, Chelsie
and Daniel Puentes.
Today we welcome Ben Hall. Ben, could you please tell us a little bit about yourself?
Sure. Thank you so much for having me. My name is Ben Hall. I'm from Grand Rapids, Michigan. I'm a third-year Ph.D. student here studying Physics and CMSE, which is Computational Math, Sciences, and Engineering.
That's really interesting. You're getting a PhD in both physics and CMSE. What does the research look like for someone that's pursuing that route?
So I came here admitted as a physics student, and as I interviewed different professors to see what type of physics research I might be interested in doing, I came across the field of quantum computing. Now, quantum computers are a new type of computer that are being built that harness the power of quantum mechanics to solve problems that today's classical computers can't solve. I had sort of a background in computation, but I really wanted to strengthen that. So that's why I pursued the dual PhD also with CMSE.
What are things that a quantum computer can solve that a normal computer can't?
Yeah, it's interesting. Some people think that quantum computers will replace classical computers, but that's far from the truth. They're only good at a very small subset of problems. One famous example, it has to do with securing your information. So if you go online, if you're doing banking or you're buying something on Amazon, your information is encrypted, sent through the internet to, Amazon, and then decrypted. The reason that that's secure is because what a computer would have to do to decrypt it is a really, really tough problem that classical computers are not good at. But if you had a strong enough quantum computer, it's been shown mathematically that with a quantum computer, one could decrypt these messages in a matter of minutes instead of a matter of thousands of years, which it would take a classical computer to do.
With that being said, how do you plan on furthering research in quantum computing? Are you actually building the quantum computers, or are you involved more with the programming of quantum computers?
For me personally, I'm more involved with the programming on the theoretical side, we would say. There are several companies and organizations that are working on building actual quantum computers. The current record holder right now, I believe, is Google, who has a 71 qubit quantum computer. And a qubit is the basic unit of information of a quantum computer, as opposed to a bit like on a classical computer. So for me personally, I'm working on, okay, once we have these quantum computers built, how can I use them in the most efficient way possible to solve these problems that we're trying to solve?
And what kind of problems are you guys trying to solve?
So for me personally, working over at the NSCL, which is the National Superconducting Cyclotron Laboratory here at Michigan State, I'm interested in solving what are called many-body nuclear physics problems. And that's very closely related to chemistry and how molecules interact. So in the future, we'd one day hopefully be able to simulate chemistries, drugs, medicine, and be able to tell if, say, how a certain drug would react to a human body without having to actually test it on a live creature.
You had mentioned how a quantum computer would be able to decrypt encrypted information a lot more quickly, than a classical computer. Wouldn't that have any threats to cybersecurity in the future, possibly?
Yes, and that's why, in fact, our federal government is very interested in quantum computing. The Quantum Initiative Bill was actually just signed into law in December of this past year, 2018. And a team that I'm on at Michigan State is currently applying for some of that funding. But yes, it would pose a threat, and whichever nation kind of gets a good enough quantum computer first will have a really great advantage. That being said, once you have a quantum computer, not only can you decrypt the classical way that people have been encrypting information, but you can encrypt your information in a new way that's not unencryptable by a classical computer. So not only do you have a sword to break down old shields, but you now have a new shield that can't be broken down by the old swords.
I feel like Ant-Man when we're talking about this, and I feel like a lot of our listeners probably feel the same way in the sense that we're just throwing around the word quantum all over the place.
Sure.
Could you give our listeners a little bit of background on what it means to actually be a quantum computer?
Yeah, so it's really funny at around the turn of the 1900s, people thought that physics was over, that it was done. In fact, I think the head of the British Academy of Sciences declared that physics was a done subject because they had discovered everything that could be said about it. Then 5 years later, in 1905, Albert Einstein, busts open the floodgates by discovering that when you really get down to a really small scale, the laws of physics that govern the universe are completely different than how we see them at a macroscopic scale. And we call those sets of laws quantum mechanics. And a lot of people, just so the listeners know, quantum is not some scary word. Quanta really just comes from the same word as quantity, because what it means is that when you really zoom in, things like energy or momentum are not actually smooth and continuous. They actually come in discrete steps. So instead of being a slide, it's like a ladder. And we say that the energies come in discrete quantities. So that's all the mystery behind the word quantum.
That was a beautiful explanation. You had mentioned about modeling the human body, and I'm a biomedical engineer, so I'm really enthralled by that. How do you guys model the human body? Everyone is so different. They have different metabolisms, different weight, height, and everything. Like, there's so many parameters that you have to look at for that.
So just to clarify one thing, mainly what we're concerned in simulating are chemical reactions, some of which could take place in the human body if you were talking about how a drug might interact. But we're not trying to replicate a person per se. What we're working on is simulating chemical systems. So right now, our computers can simulate really, really small systems if you just have a handful of particles. But obviously, in the real world, we're not just made up of the lightest elements like hydrogen, but of very complex elements, heavier elements, very complex molecules, and all the different particles that are in there all interact with each other. So the complexity and the hardness of simulating that grows exponentially with the number of new particles that you introduce on a classical computer. But on a quantum computer, it scales at a much more reasonable scaling so that we can actually simulate these systems.
I'm assuming this is to save time and money, but I would really imagine that a quantum computer is really expensive. How much do they cost? Like, will the investment in a quantum computer actually be worth it in the end?
So 2 points. One, you probably won't buy a personal quantum computer. You probably won't have a quantum iPhone. These computers are very sensitive to any external influences, and they have to be kept underground, shielded by protective material near absolute zero so that nothing can interfere with them. So how you would access a quantum computer is through the cloud, through the internet. So even right now, you can go on, for example, IBM will let you have access to one of their really small 5-qubit quantum computers, and you can actually run real physical quantum simulations on their quantum computer. So these quantum computers will be in secure, protected places, and you'll access them through the internet. In terms of the cost-benefit analysis that you had mentioned, I'm obviously optimistic, but the true answer is that no one really knows what fruits will come to bear with this new technology. I like to think about it analogous to when classical computers, or the computers that we all think about today, were first being developed. They took up entire rooms. People saw them as having no more use than solving, maybe some equations. But it no one could have predicted that you'd have computers, in yourself, in your pocket, that could communicate, across the globe in fractions of seconds, that we could solve these huge medical problems, these huge engineering problems. And so we really don't know the full extent as to what quantum computers will be able to solve. But the main areas are in simulating chemistries to help with medicine and our understanding of materials and the physical world around us, and also in machine learning. So some machine learning algorithms could be greatly assisted by a quantum computer. And so that could help us in every area, from predicting finances, economics at a macroscopic level, optimizing different problems such as traffic, or searching through databases to find the most relevant information, which could be useful, say, in a hospital when someone comes in and they give you your symptoms, and you're trying to search all these different medical records to try to figure out what's the most likely diagnosis to give them. So a quantum computer could really help in these searching algorithms and these pattern predicting algorithms, and stuff like that.
You're doing research on quantum computers, but what confuses me is this research taking place on a classical computer, or do you actually have access to any of these quantum computers that you had mentioned earlier?
Yeah, that's a great point. What's really exciting about this point in history is this is really a tipping point. The idea of a quantum computer first was thought up in the 1980s by Richard Feynman. In the 1990s, people started to work out the mathematics behind it. In the 2000s, that continued a little bit more, but now in the 2010s is the first time that we've actually had real quantum computers that have been built. So in my personal research, I do a mix of the two. A quantum simulation, if you will, something that would be run on a quantum computer, can be simulated on a regular classical computer. So as I'm testing methods to see if they work, often I will just test it on a classical computer. But the idea is that once our quantum computers scale up to a larger level, we know mathematically that they'll be able to beat out the classical computers.
Are quantum computers and classical computers ran on the same program? Like, are they Linux or Windows or whatever?
Good point. So Linux, Windows, stuff like that, that's all for classical computing. Classical computers and quantum computers are really different at a fundamental level, which I'll talk about just for a little bit. At the very basis of any classical computer are bits. As you often hear, computers know zeros and ones, right? So a zero could represent electricity not going through a wire, while a one could represent electricity going through a wire. And from that, you can combine the zeros and ones in a myriad of ways to do everything from listening to music to solving math problems. But at the very heart of quantum computers are not bits, but what we call qubits. And the only difference is that instead of it being a classical event that can be on or off, like electricity going through a wire or not going through a wire, it's a quantum event that can be on, off, or in a superposition of being on and off. So, for example, one attribute of electrons is something called spin. And all we say is that an electron could be spin up or spin down, just like a coin could land heads up or heads down. But classically, when the coin stops spinning, it's either heads up or it's heads down. But in quantum mechanics, the coin can be both heads up and heads down until it's measured. So it has a certain chance of being up, a certain chance of being down. So in a way, it's kind of like it's both up and down at the same time. And that's where the power of quantum computing comes, because you can check multiple cases at once. You don't have to check the heads case and then the tails case. You're kind of checking heads and tails at the same time. You do have to do the quantum measurements over and over, because ultimately when you measure it, either picks heads up or heads down, or the electron picks spin up or spin down. But overall, it's kind of like you're doing a lot of computation in parallel, because the coin can be in what's called a superposition of both heads up and heads down at the same time. Or, sorry, tails up or heads up at the same time. Just like a coin will be heads up or tails up in the end, if I were to ask you, is it heads or tail while the coin is still spinning, you wouldn't really be able to give an answer. You'd say, well, I don't know yet. It has 50% chance of being heads up. It has 50% chance of being tails up. So in quantum systems, that's what we have before a measurement. We don't know if it's going to be up or down, so we say that it's, in a way, both up, heads or tails. We say that, in a way, it's both heads and tails at the same time, and we can use this property to get a lot more computational power.
That was a great analogy. I'm still a little confused about what program you guys are using, though.
Right, so it'll be a completely different program from what's used on a classical computer. And that's where my research on the theoretical side comes in. How do we actually program these things? There are some programming languages that are already being developed by IBM, Google, Microsoft, that can be used to manipulate their quantum computers. But yes, you have to write whole new languages, whole new programs, because they're fundamentally different beasts, the classical computer and the quantum computer.
Do we have a quantum computer here at MSU?
Tricky question. There's a group run by Johannes Paulinen, who's a professor here at Michigan State, and in his laboratory, they're working on building qubits, which are the fundamental building blocks. You'd have to ask him on the exact progress, but we don't have a functioning quantum computer here at Michigan State, no.
You had mentioned that you're running quantum simulations using classical computers, and that there aren't any quantum computers on campus right now. So what classical computers are you using?
In my research, I will sometimes run simulations on what's called the HPCC, which stands for the High Performance Computing Center here at Michigan State. I learned how to use it in one of my classes on what's called parallel computing, which is where you get several computers. You divide up the task that you have to do and give it to several different computers so that they can give you your answer in a greater amount of time. It's kind of like going to the store and you have a shopping list, but you bring a friend along and now you guys can do it twice as fast because you divide the work in two. So I'll use parallel simulations on classical computers to get the same answer that a quantum computer would give. Ideally, the goal of this is to confirm that the quantum computer would give the right answer, and then once the quantum computers are powerful enough, we will already know that they're going to give us the right answer once we have them run problems that are too big to be confirmed on classical computers.
Is there a particular reason why quantum computers would need to be kept in such safe conditions in the first place, unlike a classical computer?
Yeah, so by analogy, let's say you were trying to move a huge rock. It would take it'd be really hard to do. But the smaller and smaller the rock gets until it turns into a pebble, even you accidentally stepping on it is going to send that rock flying. So when you get really, really small, down to the atomic level, which is where quantum computers operate, you need there not to be any interference with this system. You don't want any foots, if you will, stepping in and moving everything around. But they're so small that really seemingly insignificant events can really disrupt the quantum computer. For example, gamma rays are rays from the sun that are invisible to us, but they're showering us from the sun all the time. These don't harm us because we're very big creatures compared to the atomic level. But if one of these hit part of a quantum computer, it could mess up the entire computation. So the quantum computers have to be shielded so that these external rays don't get in and disrupt it. And they also have to be kept at a very, very cold temperature for additionally the same reason. The hotter something is, the more things vibrate around, the more likely it is that the computation could be messed up.
Does that mean that these quantum computers are superconducting then?
So, yeah, one of the bases, you could say, that people are using to build quantum computers are called superconducting qubits. There's different people working on different methods, but that seems to be the most popular one right now, and it's the one that Google and IBM are using as their basis for qubits.
Can you please explain what superconducting means?
Sure. So, superconducting, you might first wonder, well, what does conducting mean? So we often use the word conducting to say, oh, that conducts electricity, for example. So metal conducts electricity really well. That's why if there's a thunderstorm, you don't want to be near anything metal because the electrons from the lightning travel very easily through the metal, could hurt you a lot. Superconducting basically means it's the best conductor we could imagine. When the electrons are traveling through it, the resistance is zero. There's nothing standing in their way. And this is really a magnificent property, but it only occurs when you cool down your conductor to an extremely low temperature.
That's cool. Now, to clarify, you're talking about how you work with a quantum computer and how sometimes you use a classical computer to model that because we don't have a quantum computer. But are you looking at a specific thing with a quantum computing, or are you trying to figure out how to translate the classical computer to a quantum computer in just general situations?
I personally work more on the algorithmic side of, okay, once we have these quantum computers, how do we tell them to do what we want them to do? How can we most efficiently use their properties to solve problems that we want to solve? There are tons of people that are working on actually building the quantum computers. They would be described as experimentalists. So you really have to attack this problem from the two fronts.
How does this relate to artificial intelligence?
So starting off to demystify artificial intelligence a little bit, the old way of programming would be to say, hey, computer, I want you to do exactly this, but you're really fast at it and I'm really slow at it. So why don't you do it over and over again? So for example, if you're trying to tell a computer how to add two numbers together, you just teach it the rules. All of us could add numbers together, but once they get really big, it's just tedious because you have to do the same thing over and over again. Well, computers, we thought we're not very smart, but you can tell them what to do and they'll do it really fast. And that's been the main use of computers for a long time. But recently, people have looked into something called machine learning, where instead of just telling the computer how to do something, you let it learn for itself how to do it, and hopefully it will come up with a new way to solve a problem that we didn't even think of. This process requires a lot of bits. It requires really big supercomputers, as you would imagine. So quantum computing could aid in the progress of artificial intelligence by using its power in the areas that it's good at to help the classical computers with their learning, if you will.
How can it help classical computers with their learning?
So when you're trying to train an algorithm, it's called. Say, this is a really cool example. A computer beat the best chess player in the world for the first time in, I think, the 70s. But the way it did it was the old way of programming a computer, where you teach the computer the rules of chess, maybe some basic strategy, and the computer says, okay, I know how all the pieces move, I know how to win, and the advantage of having a computer is that it can look ahead multiple moves more than humans can. But recently, I think it was Google that created an algorithm that uses machine learning to try to be even better at chess. And all they did was tell it the rules of chess, but didn't tell it any of the strategy that humans had come up with over hundreds of years. They let it play itself, and every time it lost, it went back, looked at what it did, and changed things. And if that change made it better, it would remember that and do that more often. They then had they only taught this computer how to play for 4 hours. And then they pitted it against the best computer that was programmed in the old way, the one that beat the best human. And the artificial intelligence computer beat the old computer like 96 times out of 100. So that's how you, but in order to do this, to train the artificial intelligence, you have to let it, if you will, in the chess analogy, play the game of chess over and over again. And the more chances it gets to train, just like a person, the better it's going to be. Quantum computers can help the classical computer train, basically.
You just said that a computer learned in 4 hours how to basically be the best chess player and that it was able to learn over and over through experiences. What happens whenever quantum computers are a developed thing that multiple people have it in companies and then they're learning over and over? How do we make sure that they basically don't take over the world?
Well, yeah, there's been a lot of philosophical discussion about this, ever since computers were first created, but especially now that artificial intelligence is really a real developing field. And it's even more pertinent now that quantum computers are coming along and could train computers even better and even faster. My personal opinion is that technology has always come along that has shifted how humans do what we do. Whether it's a tractor for farming or a piece of paper instead of a stone tablet that you would write on. Often technology has been thought to be, ending human creativity or ending opportunities for humans because it can do them better than they can. But what it almost always has done is also opened up new opportunities for humans to do something that never would have been possible without the technology. So yes, computers were invented that can add numbers really fast and put what we call the human calculators out of a job. But someone had to design these computers. Someone had to program the computers. Someone had to market the computers. So with every new technology that comes along and beats a human at one thing, there seem to arise new problems and opportunities that humans are uniquely qualified to solve that have been introduced by the introduction of this new technology.
Is there a particular problem that you're interested in that you think quantum computers will help with in the future?
I'm really interested in what's called searching algorithms. If you go on your computer and you have a big document and you're trying to find a certain word, you hit Control F, and you start typing the word, and it comes up with what you're looking for. What's happening is the computer has to go through line by line and look for that word, and when it finds it, it returns it to you. But when you have bigger and bigger documents, more and more information to shift through, this process takes longer and longer. There's an amazing quantum algorithm called Grover's algorithm that can actually do this a lot faster than a quantum computer. And one of my favorite applications of the searching algorithm is in the medical realm. If you have a patient come in and they give you your symptoms, they have to, a doctor would rely on his or her memory and textbooks and their colleagues to diagnose this patient. But if you had a quantum computer that could shift through all the medical records of every human being, and not even in the present, but also in the past, that are stored much faster than a classical computer, it could gather for the doctor all the information that one could hope for and hopefully help the doctor give a more accurate diagnosis to the patient and help the patient get better more quickly.
How will researchers over at the Nuclear Science Laboratory on campus benefit from quantum computing being developed in the first place?
Yeah, so that's really where my passion lies, is in solving these nuclear physics problems. So over at the NSCL, they're concerned with what are called isotopes. And all an isotope is is an atom that has a different number of neutrons than protons. So in the middle of the atom, there's neutrons and protons, and the electrons whiz around outside of it. And most atoms, in their regular state, you could call it, have the same number of neutrons and protons. But if an atom gains neutrons or loses neutrons, some interesting properties arise, and that's what researchers over at the NSCL are studying. But again, the more neutrons and protons you have, the more interactions that there are between these particles, and the harder and harder it gets to simulate on a classical computer. But quantum computers mathematically have been shown that they'd be able to solve these same problems and give us new insights into the universe and how the matter that makes us all up works in a much faster time than a classical computer.
Well, it's very clear that you have a very strong interest in not only just nuclear physics, but especially how nuclear physics can be explained with the help of quantum computers. But what else do you like to do while you've been here at graduate school here at Michigan State? Is there any activities that you're particularly fond of?
Yeah, thank you for asking. Here at Michigan State, it's really fun. We actually have a physics choir. It's an a cappella group that is completely made up of all physics people, if you will, from physics undergraduate majors to graduate students like myself that are pursuing physics degrees to postdocs, and we even have a physics professor here at MSU that's part of the choir. This last semester, I was lucky enough to get to direct the choir, and so what we do is throughout the semester, we meet a couple times a week. I, myself, and some others arrange songs for the choir to sing. We practice it, we have a blast, and then at the end, there's always a big get-together of all the people in the physics department to hand out awards, to eat some food, to basically pat ourselves on the back and hang out, see everyone. And the physics choir always performs there. And every time it's been a really fun, amazing experience where we get to share the hard work that we've been putting into these songs with our colleagues.
Are there any songs that you've arranged yourself?
Yeah, so this past semester, I arranged a mashup of two of my favorite songs by Simon and Garfunkel, Bridge Over Troubled Water and The Sound of Silence.
You had mentioned that you directed the physics choir. What does it mean exactly to direct it? Are you organizing them together, or are you basically like the one orchestrating them and like controlling people's voices?
I see. So just like a sports team has to have a coach, um, any musical group has to have a director or a conductor, if you will. So what I do when I come in is I hand out the music and I help everyone learn their part. So I'll play it on piano, they'll sing it back. If it's not right, we'll work on it. And then I'm basically the person that says, okay, let's all sing it together. We're going to start on this measure. Let's see how it sounds. And then if it sounds good, we move on, and I'm the one who says, oh, let's try to add some dynamics here. Let's try to change this. This sounds a little out of tune. Let's try to fix it. But everyone is involved in, lending their own voice to create this music that would not exist with just one person.
Did you take any classes for this, or were you in band in high school or something?
Yeah, I've music has always been a big part of my life, but I fell in love with a cappella music at my undergraduate. I directed a group that I was a part of there called the Midnight Ramblers, which was so fun. We traveled all over the country during spring break to sing different tours. We entered some competitions. We sang at our school and all around, and it was just such a fun experience to bring people together for a common purpose, for music to share with other people. And so when I came here, I was so glad to hear that there was a physics choir, and so that I could continue exercising my passion even while in graduate school.
Wow, man, that's great. I've actually been to your shows before, and I think they were really wonderful. I wish you had brought something over here for us to listen to.
Well, you know what? I thought ahead, and I did bring a recording of our last performance. And what I have is the recording of my arrangement of the 2 Simon and Garfunkel songs.
Down and out, when you're on the street, where evening comes, so I will comfort you, I'll take your part, oh, and darkness comes. My old friend, I've come to talk with you again. Because a vision softly creeping left its seeds while I was sleeping, and the vision that was planted in my brain still remains. Sign of when you need a friend. I'm sailing right behind like a bridge over troubled water. I will lay me down like a bridge over troubled.
Well, I personally got to actually watch this performance myself. Hearing it a second time on the radio is actually really nice to also just, hear all the little bits that I didn't catch the first time around. So thank you so much for bringing that with us.
Of course, thank you.
And also thank you for agreeing to join us today on the radio and sharing your research not only with us, but with all of our listeners as well.
Yeah, I'm hoping that people listening learned a little bit more about quantum computers, and hopefully they won't be too surprised or scared when they really start to be developed.
Thanks a lot, Ben.
Thank you.
Thank you to all of our listeners that joined us this week. And remember, the truth is in the science. Any comments and questions can be directed to Sci-Files at impact89fm.org. We'll see you all next week on Sci-Files.